turn the screw until it wants to die and then turn it back a half. No, in order to do that correctly, you really need it. Hey guys, welcome back. Steve here with 6-Star Automotive. Today I'm going to try and catch us all the way up so that next week I can do my fuel trim video that I wanted to do. We're going to talk about fuel induction, the history of it, how it's kind of evolved from the beginning stages to where it is now with direct injection, and really hopefully catch you up on the history of where we've been and how we got to where we are today. So before we get started, please like, subscribe, and join me as we talk about the history of fuel induction. So over the years, fuel induction techniques have evolved from miniaturized marvels of mechanical engineering known as carburetors into the computer-controlled precision of electronic fuel injection. So instead of breaking this up into a bunch of different videos, I'm going to try and get most of this done in one. So let's start off with the carburetor era. This is about late 1800s to 1980s. Carburetors mix air and fuel mechanically based on vacuum and pressure differentials. It works off of something called Bernoulli's principle and the Venturi effect. The Venturi effect is a phenomenon where a fluid, either a liquid or a gas, flowing through a constricted section of a pipe experiences an increase in velocity and a decrease in static pressure. This effect is a consequence of Bernoulli's principle, which relates the velocity, pressure, and elevation of a fluid in motion. Essentially, to maintain the same flow rate when a fluid encounters a narrower space, its speed must increase, and this increase in velocity is accompanied by a drop in pressure. So you probably heard about carburetor jets. So carburetors don't have jets. A jet would basically think of some sort of an injection device or something. They don't have that. They basically have orifices, and it uses the Venturi effect, which as the air goes through a smaller orifice from atmosphere down into the carburetor itself, it has to speed up in order to go through air, which creates a low pressure zone in that area. If you put jets, orifices in that area, it's going to cause a vacuum or a low pressure right in front of that jet and pull that fuel in. So the fuel pressure in a carbureted system is extremely low. It's like 4 to 7 psi. The fuel pump's only job is to get the fuel from the tank into the bowl, which has a little float valve. So as the fuel pumps into the bowl, the float comes up, shuts off the fuel. As the jets pull the fuel out of the bowl then gets lower, drops that float, and then that allows the fuel to flow back in until it reaches back up and shuts it off. So you've smelled carbureted cars that they drive past. It's a cool, nostalgic smell, but it is terrible. I mean, what you're smelling is unburned fuel. They required constant adjustment and tweaking and twacking and special tools and screwdrivers that bend around in a circle and like snake like an S. And older guys will think that, carburetors were so, no, they weren't easy. They were definitely not easy, and they were absolutely not efficient. It's not like you just turn the screw until it wants to die and then turn it back a half. No, in order to do that correctly, you really need a 5-gas analyzer. So you need to see how much oxygen, how much carbon monoxide, how much carbon dioxide, and how much hydrocarbon is in the exhaust in order to really know what it's doing and how it's burning it. Mechanical fuel injection, like almost all technology, especially automotive technology, it was developed because of war. World War II, mechanical fuel injection was designed for aircraft in order to get them to work better at higher elevations. It did offer greater precision and adjustment than carburetors, but it was much more complex and expensive. So early EFI, or electronic fuel injection systems, came about in the 1970s to the 1990s. The 1970 Clean Air Act really pushed this transition into electronic fuel injection. The advent of the microprocessor, electronic sensors, and the electronic control units really made this system possible. The earliest fuel injection systems were known as throttle body injection. So basically the same principle as the carburetor, and rather than relying on the Venturi effect, it had a pressurized fuel system that would spray at different pulse widths, we'll get there in a little bit, into the throttle body assembly. So it's one injector in the throttle body, and then it kind of just disseminates throughout all the cylinders on its own. So after throttle body injection, we moved to what's called multi-port fuel injection. You've probably heard that before. Multi-port fuel injection moved the injectors down to each individual cylinder, into the port before the valve. What that allowed was for much greater precision. Instead of the fuel just spinning around in the intake and pooling inside of the intake manifold, it's directly in front of the valve, which allows it to be much more efficient and less wasteful. As ECUs became smarter, we transitioned into what's called sequential fuel injection. Sequential fuel injection allowed for the pulsing of injectors one after another, timed to match the firing order of the cylinders. This contrasted with older systems like Bosch's K-Jetronic that sprayed fuel simultaneously or in groups. By precisely timing the fuel delivery to each cylinder, sequential fuel injection improves fuel efficiency, reduces emissions, and enhances engine performance. So in order to know how much fuel to put into the system, it has to know how much air is coming into the system. So a stoichiometric air-fuel ratio is 14.7 to 1. So that means 14.7 parts of air to 1 part of fuel. Of course, this isn't 100% all the time, because if you're running a colder engine, you need to be richer, and if you're, anyway, generally speaking, that 14.7 to 1 is what you're looking for complete combustion. So in order to determine the amount of air that goes into the system, we had a couple of different ways of doing this. Well, there's a lot of different ways, but I'll go over the two most common. So there's a MAP sensor and there's a MAF sensor. You probably heard both of those. You have manifold absolute pressure sensors that work off of vacuum, and then you have mass airflow sensors that work off of the volume of air that comes in. The mass airflow sensors are so cool. So they have a little, generally speaking, most of them have a hot wire. The hot wire it has a certain amount of amperage that goes through that wire in order to keep the wire at a certain temperature. As the air goes past it, it cools the wire. The wire then has to increase the amperage going through it in order to make that wire stay at the same temperature. So it can tell very precisely how much air is coming in, not just that air is coming in. It's really neat. So knowing how much air is coming in helps us determine how much fuel to put in, and that's all well and good, but it really doesn't tell us what happens. So we can determine what's going to happen. Here's the air, here's the fuel, bang, but then how did we do, right? So in order to know that, and in order to make it what's called a feedback system, or a closed loop system, you have to have something in the exhaust saying, okay, this is what happened. So this is what you thought was gonna happen, but this is what actually happened. And that's where the oxygen sensor comes in. So it's kind of a silly name. I actually remember taking a couple of classes about oxygen sensors, and they're really technically not oxygen sensors. They're really hydrogen sensors. It really doesn't actually matter, and it makes a lot more sense to think of them as oxygen sensors. You have less oxygen on the inside of the sensor and more oxygen on the outside of the sensor. That induces a voltage inside of the sensor. Textbook speaking, that is the way that they want you to think it works. It's not actually how it works. There's some really cool articles out there. If you dig really deep, you'll find them. It doesn't really matter, but all that matters is that it determines how much oxygen is in the exhaust to determine how complete the combustion event was. So is it rich, is it lean, and that's kind of how it works. So we talked about moving from carburation, which is basically throttle body injection, to electronic throttle body injection, and then down into individual port fuel injection. And that's cool. So what we're doing is we're getting the fuel closer down to each individual cylinder. So the next logical progression, if you think about it, is direct injection. So instead of wasting fuel, even in the small amount that we're wasting with port fuel injection, as it kind of sticks to the intake and gets splattered against the back of the valve, if you spray the fuel directly into the cylinder, you really aren't wasting anything, and you can get much better fuel economy. Of course, if all you're chasing is fuel economy, you don't really think about all the other aspects like dirty valves and buildup and all the, it has its problems. It absolutely does have its problems. It's not a flawless system, but when it comes to efficiency, it's really about as good as it gets. You cannot get any more direct than direct fuel injection. Alrighty, I probably melted your brains enough, and I apologize, but as you can probably tell by now, I love this stuff. I've been learning this since I was 14 years old. This is the only job I've ever done. This is the only job I'll ever do. I love diagnostics. I love understanding how these systems work. I love helping people with this information, and I really love Sandpoint. So I'm glad to be here with you guys. Thanks for watching this video. Next week, I'm going to get to that fuel trim video so we can really understand kind of how all this stuff is working. Until then, have a great week, and always remember, you can come by and experience a 6-star difference for yourself.